Imagine flying a multi-million-dollar commercial airliner from New York to London, and upon landing, immediately pushing the aircraft into the ocean. For decades, that is exactly how the aerospace industry operated, with every single launch. NASA attempted to solve this massive waste with the Space Shuttle program, but the shuttle was a partially reusable system that functioned more like a refurbishable one. Every time an orbiter returned to Earth, it required up to 500,000 labor hours to recertify for its next flight. The thermal protection system alone demanded 80,000 hours of meticulous maintenance. This logistical burden kept launch costs at roughly $54,500 for every kilogram of payload delivered to orbit. To the industry of the time, the shuttle's massive upkeep suggested rocket reusability was a financial dead end, rather than a viable path forward. The reason reusability is so difficult comes down to a mathematical trap known as the tyranny of the rocket equation. This chart shows the massive velocity requirement of 9.5 kilometers per second needed just to reach low Earth orbit. By the time a rocket carries enough propellant to reach that speed, the mass remaining for the actual payload is tiny. If you want to land that rocket back on Earth, you have to add heavy landing gear and hold back propellant for the return trip. As we factor in the mass of those legs and the return fuel, that already thin payload capacity often disappears entirely. Breaking this cycle required a total redesign of the descent process. Instead of simply building a sturdier rocket, engineers changed the mechanics of how a cylinder interacts with the atmosphere when falling from space. The return journey begins the moment the stages separate. The first stage booster, 47 meters tall and weighing 25 tons, is falling at hypersonic speeds in a near vacuum, where traditional wings or flaps have no air to push against. To orient itself, the booster executes a 180-degree flip maneuver. It uses a cold gas reaction control system, firing small, pressurized bursts of nitrogen to swing the heavy engine section around so it faces the direction of travel. Once aligned, the booster ignites its engines for a boostback burn. This reverses the rocket's horizontal velocity and directs its ballistic trajectory back toward the landing zone. This simulation shows the entry burn. As the rocket hits the denser atmosphere at supersonic speeds, throttling 3 engines creates a physical aeroshield out of superheated plasma. The outward pressure of the exhaust plume physically deflects the destructive bow shockwave away from the rocket's skin, reducing peak heating by 30%. Using the rocket's own engine thrust as a dynamic heat shield removes the need for heavy, fragile thermal tiles. This eliminates one of the biggest refurbishment bottlenecks that made the space shuttles so expensive to fly. Once the booster slows down and enters thicker air, it begins its unpowered atmospheric descent by deploying 4 titanium grid fins near the top of the vehicle. These grid fins utilize an open, cellular lattice structure. As air forces its way through the grid, it creates stabilizing aerodynamic drag. Because this drag is applied at the top of the rocket, it keeps the heavy engine section pointing straight down toward the target. Early versions of these fins were made from aluminum, but they often melted during re-entry. By switching to cast titanium, the fins can survive the extreme heat and be flown repeatedly with almost no maintenance. Manipulating the atmosphere for steering allows the booster to conserve its extremely tight fuel margins for the final critical landing sequence. Landing a nearly empty rocket is mechanically complex because a stable hover is impossible. The lowest possible thrust of a single engine is still greater than the weight of the nearly empty rocket. If the engine fires for a fraction of a second too long, the vehicle will climb back into the sky. To solve this, the landing system relies on an autonomous algorithm known as G-fold, developed by NASA's Jet Propulsion Laboratory. This animation illustrates how G-fold utilizes convex optimization. Bypassing the limitations of older Apollo era software, it calculates the most fuel-efficient landing trajectory in real time, actively shrinking a trajectory path down to a precise 0 point on a target grid. It executes a maneuver called a hover slam. The algorithm times the center engine burn so that the rocket's downward velocity reaches exactly 0 at the precise millisecond the landing legs touch the deck. When landing on a drone chip in the open ocean, the top-heavy booster is vulnerable to rolling waves. An autonomous robot called Octograbber drives out from a blast-proof garage, slides under the rocket, and clamps onto the engine structure to anchor the vehicle against the ocean swells. Combining predictive descent software with robotic deck recovery removes the need for human crews on the landing deck. This allows for a much faster turnaround between flights and dramatically improves recovery safety. This approach has transformed the cost of spaceflight. The cost per kilogram to orbit has dropped to roughly $2,500, with individual boosters now flying up to 36 times and returning to the launch site in just 14 days. Even with these margins, landing legs remain a significant disadvantage. Every kilogram of leg hardware is a kilogram of payload that cannot be sent to orbit. The next iteration of reusability, seen in the Starship program, utilizes a recovery method known as Mechazilla. The launch tower uses giant mechanical arms to catch the descending booster in midair before it ever touches the ground. Catching the booster eliminates leg mass entirely. It also allows the vehicle to be placed directly back onto the launch mount, creating a system for rapid, full reusability. While cheap satellite launches are the immediate benefit, Earth recovery serves as the foundation for a much larger shift in deep space logistics. When upper stages are fully reusable, orbital propellant depots become a reality. Spacecraft can park in orbit and have cryogenic fuel transferred directly into their tanks from reusable tanker flights. Orbital refilling bypasses the physical limits of launching everything at once from the ground. It is the final step in breaking the tyranny of the rocket equation, opening sustainable two-way transport corridors to the Moon and Mars.